I am beginning to record. So hello everybody, welcome to Chem 3 lecture. Tuesday, March 17th, thank you. Wonderful. So take a look up here, I'm glad everyone's commenting. So you do need to comment to make sure that you get participation credit for today. So either commenting or asking a question, and I'm going to be going through the log so that I can tell who was participating. So if you all don't mind turning off your microphones, please turn off your audio. Just click mute at the bottom left of the page.
Okay.
And what we'll do is just whenever you have questions, so I'm just going to keep it muted for everyone since we have, however many tens of people here. So we're just going to, when you have questions, you just ask me over the chat, okay? And that sounds good. Okay, great. And you can either chat to me privately or to everyone. And awesome. Great. So I'm glad everyone's here today. We are recording and we don't have the 40-minute time limit that we would have had with Zoom. They've lifted it to make for these circumstances now. So those are my two notes. Again, everyone must comment, right? My two announcements, and that note up top to record was for me. Does anyone have questions before we begin about logistics, about quiz tomorrow, anything? And again, reminder, please turn off your microphone. Turn off your audio, please. But when you have questions, you can type it to me or to everyone. Don't be scared. Don't be scared. I know. It's okay, though. Like, it's going to be okay. It's going to be okay. We're here. Look, I'm in my living room. I'm in my bar right now. Like, if you can see, I'm not going to move the camera because it's good right now. But like I have this bar with this setup. There's a sink right here, which is perfect for my demo in a second. I've got my whiteboard that I took from the STEM Center. So we're figuring it out. Okay, we're making do. All right, other questions? Any questions? Okay, estamos aquí. Do we need to print out the exam? So I'm not emailing you anything. The quiz is going to be online, on Canvas. So Thursday's quiz will be on Canvas. If you get extra time on the quiz, email me replying to the message that I sent that says updates, please read, and I'll be able to give you extra time. Yeah, can everyone please mute yourself? Please click mute on the bottom left of your page, please. Everybody, please mute yourself, okay? Yeah, and the instructions for the quiz will be posted, I'm pretty sure, right? Has anyone noticed, can you see? I'm pretty sure, as far as I know, that you can see quiz instructions even before it's available to take it. Has anyone, right, it's not on the module yet. I'm not talking, it's not there yet. I haven't made it yet. I'm just saying that normally, I'm pretty sure you can see instructions before it is live and like available. So either way, I'm giving you extra time though, giving everyone 15 minutes instead of 10 to take the quiz. And again, just follow the instructions. For each question, you're going to be uploading a photo of a structure for the first problem. So make sure you follow the instructions on how to do that, and I'll be posting them in the question. Okay, good. So you can see the instructions before you click the start button. So then that's good. And then that means that tomorrow late morning, I'll be able to get that up there for you. I have a full day today. So tomorrow after like 11, I'll be able to do that for you. Okay. To get that up so you can get ahead of time. Okay, ¿quién está hablando? Por favor. Los podemos escuchar. Gracias. Okay, bueno. All right. Okay. Hay otra gente. Okay. So we're going to continue where we left off last time. So Yes, you can take the quiz before you begin class. That's what we'll do is we'll have it start like at the normal class time. We'll have it start at 11:15 to 11:30, and then we'll begin lecture after that. Okay, so let's see if you can't see me or hear me. The online quiz will be where they normally are where they normally are. Oh, the online quiz, excuse me. So Jesus, do you mean the quiz that is normally in lecture that we're taking online? That's going to be in the week 8 module where it says lecture quiz study guide. It'll be run under that. Thanks, Elena, for helping Lexi. Okay, other questions? I know, I can't find the way to mute everyone. On the other version I could, and I don't know how to do it right now. So please, everyone, mute your microphone. Yeah, that one will be in week 8, okay? The quiz, Thursday's quiz will be in week 8. Okay, other questions? Okay, so we're gonna continue. I'm gonna change the mic and we're gonna just continue on the worksheet that we were working on last time. So you're gonna see what I see. Is that, I know it's blurry, hold on. Is that the right way for everyone though? God, that's so hard. Okay, good. Let's try to get it unblurry. Okay. Okay, that's gonna be harder than I thought. Okay. Okay, so I know, yeah. Maybe trying to focus on that. Okay. Let's go really close. Okay. So we I don't have any option. Oh my god. Oh my god. Okay, so I think I'm just gonna like try to hold it. Let's do that. Okay. There we go. Oh my god. It's all opposite for me. Y'all have it like the right way, but it's all opposite for me and it's insane. Okay, so we are going to figure out if molecules are polar, right? We ended with determining if individual bonds are polar, right? But we need to figure out if the whole molecule is polar. That's the next step, because that's the most important piece of this, right? Like if the whole molecule is polar or not. And then we're going to move on today to determining intermolecular forces. This is so important. Like I said earlier, like electronegativity is one of the most important concepts in chemistry. So is polarity. If molecules are polar or not, that tells us a whole bunch of other things about the molecule and the types of forces that it displays, whether it's a solid, liquid, or a gas, how it reacts, and all kinds of stuff. So, all right, so we're gonna figure out, like I said, if molecules are polar or not, and we've got, 1 second here. So I was drawing the polar bonds in red, and I'm going to use purple to show like overall polarity. Okay. So let's start with, we started with methane last time, right? So on the back side here. And we said that methane has no polar bonds, right? Because the electronegativity difference between the carbon and the hydrogen was too small to call that any polar bonds. And so if there's no polar bonds, can the molecule be polar? Type in your answer. I guess what I should ask is, if there's no polar bonds, is it a polar or non-polar molecule? Thanks for all the no's. And so can you type also, is it polar or non-polar? Oh my God. Yeah. Awesome, everybody. Yeah, so methane is a non-polar molecule. So we're going to write in here, for methane, non-polar. I know it's blurry, everyone. I'm so sorry. All right. So methane is a nonpolar molecule. Here's methane, right? Showing the model here. And none of the bonds were polar, right? That means then are electrons evenly shared between the carbon and the hydrogens here? Are the electrons evenly shared in this covalent molecule with the covalent bonds? What do you think? Are the electrons evenly shared? I appreciate the suggestion. And Yanid, I just want to try doing this for a second. That's okay with everyone. I know it's not the best. Yeah. Cool. The electrons are evenly shared. Wonderful. Okay. Okay, let's see, I'm gonna mute everyone that's not muted. Cool. All right, so then let's move on to another molecule. Let's try this one over here. So looking at water, right? Water up top here. So we said that there were two polar bonds for water, right? And so looking, right, at whether the whole molecule is polar, we have to determine the shape of the molecule. So whenever we see that there's more than one polar bond, we have to look at the shape of the molecule. So if I come over here and say I don't know the shape of water, right? And say I just think that it looks linear, like I drew it in the Lewis structure, right? I would draw my vectors, my polar bond vectors like that, right? And would those vectors cancel out the way that I drew it linear? Would those vectors cancel? Would they be going in equal and opposite directions? Yeah, good. Exactly. Thank you everyone for responding. But that's not the shape of water, right? This is the shape of water, right? Water has a bent shape. And so when we look at the polar vectors and this bent shape of water, do they cancel out? Are they going in entirely opposite directions? Do they cancel? Right. Exactly. Thank you, everyone. They wouldn't cancel. So then over here, right, when we say, is water a polar or nonpolar molecule, what do we write? Right. We write polar. Right. Water is a nonpolar molecule because the polar bonds do not, and actually I want to erase that and say the polar vectors, right, with a magnitude and a direction, the polar vectors do not cancel. Okay, so we said it was a polar molecule. The polar vectors do not cancel for water. Okay, yeah, the bonds are polar, right, and the molecule is polar. And so then over here, when we have an overall polar molecule, what we can do is draw another dipole arrow that shows the overall direction of polarity for the molecule. So overall, this molecule, right, has an uneven sharing of electrons, where overall we're going to see more electron density up top near the oxygen and less electron density down below near the hydrogens. And what we can do is draw a symbol that represents that. And this symbol is a lowercase delta, and that means partial. A partial negative charge is up by the oxygen because it has more electron density. And there's a partial negative, or excuse me, a partial positive charge down by the hydrogens. So down here, there's a partial positive, partial positive. Yeah, exactly. The shape of the molecule, right, affects the polarity of that molecule. So tying it all in together right now, right? So questions on water. So water is polar, and let me show you, like over here, wherever we see a polar molecule, we'll be drawing the dipole arrow, right, the dipole vector in purple and big and fat like that. Okay, questions here? These pens are friction by Pilot. And everyone, when you get these pens, you can get refills, so you don't have to waste the whole barrel. You can buy refills for so much cheaper and less plastic. Yeah, the electrons in water, right, in the bonds over here, are being pulled toward the oxygen. Let me show you, oh, the big arrow. The big arrow here shows the overall polarity of the molecule. You can buy the pens at Palace if you want. The big arrow here affects the the big arrow is showing the overall polarity of the molecule. Yeah, but shop local, Kelsey, shop local. Right? The big arrow here shows the polarity of the overall molecule. Jesus. So we're showing here the shape of the molecule is affecting the polarity. So we're showing that overall there is a polarity of the whole molecule because of the shape of the molecule. If water was linear, these polar vectors would cancel out, the ones that we drew in red up here, because they're equal but opposite, right? Do you see how they would cancel here? Right? But, exactly, but in the actual shape of the molecule, right, water is bent, right? Here's water. Water is bent. Oh my gosh, it's supposed to focus. All right. Water is bent. So that means then that in reality, those polar vectors do not cancel. There's an overall motion, like directionality of the polar bonds toward the oxygen and up, right? Because the bonds are moving upward in that bent shape toward the oxygen. It can be down to, it can be to the side, whatever, right? It's all going to be an overall, right, pull of electron density toward the oxygen. The oxygen is more, yep, greedy or hungry for electrons, right? But then it has to do with the shape to see if the whole shape you do, okay, right? So like overall, and that's why we're drawing, so this purple arrow here is representing the overall shape of the molecule, lending the polarity to the overall molecule. So let me show you, I'm gonna screen share different right? So here's some images that we can use to think of the polarity of water. Up there is hydrogen, H2, where there's no separation of, or it might be O2, I'm not sure, but there's no separation of electron density. But then on these diagrams here, right, on these electrostatic potential diagrams, right? This is an electrostatic potential diagram, which is showing the red region having more electron density and therefore a partial negative charge, right? And the blue region showing less electron density and showing a partial positive charge. Here's the ball and stick models, right, of water, right, showing each individual polar vector. And then here's the ball and stick model of water showing the overall polarity for the molecule. So polar bonds up here, polar molecule down here. The F symbols are actually lowercase delta. It's a lowercase delta, and it means partial. Exactly. So a delta minus is a partial negative charge. A delta plus is a partial positive charge. Okay. So water is a polar molecule, which makes it so important, everyone. The fact that water is polar means that it has stronger forces holding water together, and water would not be a liquid if it were not polar, if it wasn't for its bent shape, right? Water would not be a liquid, it would be a gas. But as we'll see later today, water has a really important intermolecular force that holds the molecules together in the liquid phase. So important. All right. What about, let's do this one down here. Let's do nitrate, NO3 minus. So we said that there were 3 polar bonds, right, for nitrate. 3 polar vectors that we drew, right? One for each bond. And now we want to see, is the overall molecule polar? So the question that we're asking is, do the polar vectors cancel out? Do the polar vectors cancel? Tell me if you think these polar vectors cancel for NO3 minus. Okay, so I'm getting many no's, a couple yeses. All together, do these, right, these dipole vectors cancel out? Think of it this way. If I were to pull like equally on each of these bonds, right, if I pull 2 of them, I've kind of got like a downward flow, right, kind of like a bent downward directionality of electron density. But as soon as I've got that other one, that third, right, actually, if we were to like pull on each of these bonds here, right, we would actually see that they are equal and opposing, right? So these bonds actually do cancel. These polar vectors actually do cancel. This is the time where I usually lie on the table in lecture and have people pull on my legs for one bond and each of my arms for the other bond, and they pull me and I do not move because the way that they're pulling me, right? So picture these are my legs, right? And my arm is one arm and the other arm. And picture me being pulled, right, in opposite directions. I don't move on that table. So these polar vectors actually do cancel. So imagine like that's my head right here. These are my legs. Okay. So I wish I could show you that, but do you see that a little bit? Like if I just take these 2, like I'm kind of pulling down, but as soon as this one gets into the picture, right, they actually are equally opposing to each other. Yeah, exactly. So overall, this trigonal planar shape, right, with all 3 polar bonds means that it's a non-polar molecule. Exactly. They cancel because of the shape of the molecule. Iris, is this shape bent or is it trigonal planar? Love the light bulb. It's trigonal planar, exactly. So if it were bent, and we'll get there in a minute, if it were bent, it would be polar. But since there's another bond with a polar bond, right, another vector tugging, and we're not thinking, I mean, I use this analogy, right, as movement, but really we're thinking of just like overall there's electron density here, here, and here. Overall, there's no like one side of this molecule doesn't have more electron density than the other side. Do you see that? Like overall, there's the same amount of electron density all around the outer atoms. Okay. So cool. So then let's write that down here. So for here, for NO3 minus nitrate, it's a nonpolar molecule because the polar vectors do cancel. So overall, there's no one part of the molecule that has more electron density than the other part. Like one side, I should say. If there's one side of the molecule, yeah, here's the Lewis structure. Well, now you remembered. But who is who's Savis? Everyone, that reminds me, I do need to see your name that I know so that I can give you credit. Who is that? Savis? Oh, okay, great. So make sure that you change your name, or I guess I'll remember, but if you have a nickname on there, please change it to your name so I know. It does. Thank you. Yeah, Jesus, you're good. All right, so other questions on nitrate? So next time we meet, I'll get on the table and you can pull my arms and legs, okay? So if the charges point away from each other, it will be the same, or does the magnitude? That's a good question. The magnitude does matter, but we're not going to be getting into those examples in this class. So say instead of say you had a sulfur here, right? Instead of an oxygen, then yeah, there would be overall more electron density toward the oxygen because they're more electronegative than sulfur. So the magnitude does matter, but in our class, we're only going to see, we're only going to have to make decisions based on the same magnitude, okay? Is that better, Brianna? Good question. So let's do NO2 minus on the next page. Nitrite instead of nitrate, right? So now, right? Now, so let me just pop off, ready? I'm just going to pop off one of these oxygens, one of the bonds for nitrite. Now, is there an overall, now those polar bonds that we didn't get here, we didn't draw the dipole vectors on this molecule, so let's do that. So I'm going to put this up here, and let's draw the dipole vectors here. So do they go toward nitrogen or toward oxygen? Yeah. Toward the oxygen. Oxygen's more electronegative, so it's more greedy for electrons. So we can draw the two dipole vectors like that, right? And so now for NO2, with one of the bonds removed, exactly, good. With one of the bonds removed, now do these polar vectors cancel? Do these polar vectors cancel? Yeah, cool. So I'm seeing lots of no's. So the reason that they go toward the oxygen is because oxygen is more electronegative, okay? Oxygen is more electronegative, and that's what that means. That's okay. If y'all don't know, no problem. So more electronegative, that means that that's the direction of the electron density, right? More electrons are the electron density is being tugged toward the oxygen, right? There's more electron density, more probability that there'll be more electron density around the more electronegative atoms. So that's why we draw the dipole vectors pointing toward the more electronegative atom. Hi, Uriel. Does that make sense? Jesus, when you had that question? Okay. So then back to the question of whether these dipole vectors cancel. Think of it like this. This one's going down and to the left, right? This one's going down and to the right. The way that they would have to cancel is if one was going down to the left and the other one was going up to the right. So imagine the directions being like opposites of each other, right? This is down left, this is down right. So there's two downs in what I just said. And so overall, there is an electron density facing down. Does that make sense? Like, think of it like, say it to yourself, like down left, down right. So two downs, right? If that helps, I'm not sure. But we can also show you like, so here, right? So if I were to like tug on these polar bonds and I'm showing like their, right, oxygen has more electron density, there's nothing else pulling up this way.
Good,
So is this a polar molecule or a non-polar molecule?
Yeah, they're kind of talking about like closing the Pizza My Hearts, but it hasn't happened yet, so.
Polar or non-polar molecule? Thank you everyone for muting. I'm trying to mute that person and I'm not seeing a button to do it for some reason. Maybe they don't have a camera. I mean, maybe it's not that person and they don't have. Okay, I'm muting people. Mute. Okay. Polar, it is a polar molecule. Okay, so overall, right, there is a polarity of the molecule toward the oxygen. So we can draw a overall, right, for the molecule, come on. Thank you. For the molecule, right, we can draw an overall dipole arrow showing that it's going toward the oxygens. And so that means then on this side of the molecule, there's a partial negative charge, a little delta minus, right? And on this side of the molecule, there's, I take that back. Pardon me, y'all. I did that wrong, right? I put a partial negative on the nitrogen, but it should have been a partial positive. Partial positive on the nitrogen and partial negative on the oxygen side of the molecule. There's a lot of marking up on these molecules, I know. That's why it's so important that you do this again for each of them, right? You should like go through the steps again for all of them. No, thank you, Diego. The type of bond doesn't affect the magnitude. So a double bond or a single bond doesn't affect the electronegativity for the atom. Thank you. So let's move over here, and we want to say that nitrate, in fact, is polar. Because the polar vectors do not cancel. You know that oxygen is partial negative because it is more electronegative. So that means there's more electron density down by the oxygens than up by the nitrogen. That's why. Okay, oxygen is more electronegative, so that means it has more negative charge, so it's a partial negative charge. We're going to do NF3. We're going to do NF3. Yeah, let's do another one and we'll see if canceling helps over there. So here on NF3. So we said, right, that we've got, so the question, can the arrow go both down and up for polar on water? Yeah, do you mean the big purple arrow? The big purple arrow just points in the direction of the electron density, right? So there's a partial negative charge up here because we're showing that the polar bond vectors are pointing toward the oxygen, which is more electronegative. And so that means overall, the molecule has more electron density toward the oxygen, right? It doesn't matter whether it's up or down, it just matters that you're pointing it to the correct side of the molecule. So that was for oxygen because we're pointing it toward oxygen. I mean, excuse me, that was for water because we're pointing it toward oxygen, which is more electronegative. Whereas here, right, same thing. We just, the way that we drew this molecule, and it's the same way, like you can draw it any way you want. You can draw it upside down, right, to the side, whatever, as long as your overall purple arrow, the one that's showing the overall polarity of the molecule, is facing toward the more electronegative atoms, then you're good, right? So here, it's facing down, pointing down because oxygens are more electronegative. So overall, there is a separation of electron density with more electron density toward the oxygens. The arrows go toward the atoms. Be careful, Jesus, that they go towards the atoms with the more electronegativity, exactly. That's all good. Exactly. Okay, great. No problem. All right, so let's go to, this is a good one, NF3. Actually, yeah, let's do NF3. All right, so we said that we've got 3 polar bonds, 1, 2, 3, right? So overall, is there an overall separation of electron density for this molecule? Meaning, do those polar bonds cancel or not? What do you think? That's on the chart, on the electronegativity chart right here, right? Those electronegativities come from this chart here, which you have on Canvas. So do these polar bonds cancel? Thank you for answering. Do these polar vectors cancel? All right, great. So that's again where shape comes in. Thank you, everyone. Good. They do not cancel. If this were trigonal planar, right, then they would, like me on the table. If my arms were 2 bonds and my legs were another bond, then they would cancel. But it's not trigonal planar, right? It's not in a plane, it's trigonal pyramidal, right? It's in a pyramid. So overall, right, when we see this model here, right, is there an overall direction to the electron density, right? The fluorines are on the outside. So overall, right, there's a, sorry, it's hard to do this opposite. Overall, right, there is in the molecule, right, exactly, in the molecule, overall, there's more electron density on one side of the molecule, and it's on the side where the fluorines are. Exactly, it all depends on the shape. So this is trigonal pyramidal. And so in the model, we see that there's an overall separation of electron density toward the fluorines, right? That means it's toward one side of the molecule because of its trigonal pyramidal shape. So overall, right? We see that yes, nitrogen trifluoride is polar. Because the polar vectors do not cancel. Right. So wherever you see a big purple arrow, that's where the molecule is polar. Wherever you see the red vector arrow, that's where the bonds are polar. And that is good. So there's a lot of practice on this worksheet, right? And there's so much more practice on the back, right? So you've got lots of opportunities for practice. Sorry, everyone. That should be... Anyway, all right. The quiz, whatever's on the, thanks, Johnny. So whatever's on the quiz study guide will be on the quiz. I can't say I don't remember right now, I'm sorry. I don't remember what's on the quiz and what's not, but whatever's on the study guide will be. Okay, that is not focusing. I don't know why. Okay, so, all right, so here, let's move on to, and you can do carbon dioxide, right? You can tell if carbon dioxide, if those vectors cancel. So is carbon dioxide a polar or non-polar molecule? Dashes, I'll get to the dashes. Is carbon dioxide polar or non-polar, the whole molecule? Okay, I'm seeing pretty much half and a half here. So remember, the question that you want to ask is whether the vectors cancel. Are these going in equal and opposite directions? Do they cancel? Right? If they do cancel, then overall, there isn't one side with more electron density than the other side. Good, so they do cancel. Exactly. So that means then that there's no electron density, there's no more electron density on one end of the molecule than the other end of the molecule. Unlike water, right, where we did see, right, overall there's more electron density up toward the oxygen. But for carbon dioxide, the shape of it, right, carbon dioxide is linear. So those polar vectors cancel. But water is bent. So those polar vectors do not cancel. Yeah, water's bent. Water is polar. Exactly. And carbon dioxide, the whole molecule is polar. It does have, nonpolar. The whole molecule is nonpolar. It does have polar bonds, which we drew in red with vectors, but the molecule is not. Woo! What was I saying about water? Water is bent. So there's more electron density up toward the oxygen, right? If water were, right? If water were linear, right? If I could if water were linear, then those polar vectors would cancel, but they're not. They don't. Water is bent. So overall, more electron density up toward the oxygen. So question was on this side, Dashes. This one here, is that the dash you mean? Okay, back page. This bond is a bond. Is that what you mean? That's a bond. Mm-mm. Mm-hmm. Mm-mm. That's a bond. All right. Cool, so you've lots more practice. Lots of fun practice. Does it affect the overall structure in this case? Does what affect the overall structure? The fact that it's polar or nonpolar? Oh, you mean this bond right here? Is that what you mean, Alberlinda? Like, okay, it does affect it. Well, you're just gonna bond the way that it's laid out here with nitrogen attached to nitrogen and a hydrogen on each nitrogen. And then you're figuring out the Lewis structure and the shape for each nitrogen because there'll be 2 central nitrogens. Right? Like hydrogens are on the outside, nitrogens are attached to each other. Yeah. Will you get instructions via email on what you can use on the exam? So on the quiz tomorrow, you'll get the periodic table. On the quiz Thursday, you'll get a periodic table and you'll get this chart. You will get that chart. You do not have to memorize these. That would be crazy. Would we determine polar or nonpolar by the electronegativity? Yeah, you do have to remember this though. You do have to remember that. You're not going to get that, right? And that's really the only 2 that you need to remember for this class. Okay. So I don't know the green and yellow chart. I don't know what you mean by that. All right. How do you know which direction the polar vectors go? Yeah, no, toward the more electronegative, Mary. The more electronegative. It's showing that the more electronegative atom has more electron density. So the vectors go toward the more electronegative atom. That's showing that the electron density is being attracted to the more electronegative atom. Yeah, good, George. That works. All right, so everyone, we got to continue. We have another worksheet. Who has the intermolecular forces worksheet? We have this one. Ooh, okay, great, everybody. Okay, so now we're moving on to this because it is so directly related to polarity of the overall molecule. So learning what we have so far, these are called intermolecular forces. So intermolecular forces are like the attractive forces that we talked about on the very first day when we were doing that demonstration with the candle underneath the beaker, and we talked about solids, liquids, and gases and how the forces between the molecules dictate whether something will be a solid, liquid, or a gas. And this is what we're looking at here. Now we're halfway through the semester, and we're now looking at the types of attractive forces that exist between molecules. So that's why we call them intermolecular forces, between molecules. So there's one type of intermolecular force called London dispersion. And London dispersion forces are the weakest intermolecular forces, okay? they they exist for all atoms as well as covalent molecules. So when you're asked on a quiz or your homework which intermolecular forces are present in a molecule, always for covalent molecules and individual atoms, London dispersion forces will exist. And London dispersion forces, and so that's the weakest. And then another overview here. So dipole-dipole forces, that's intermediate. That is like in between the weakest and the strongest intermolecular forces. And dipole-dipole forces come with all polar covalent molecules. So all molecules, whether they're polar or nonpolar, have London dispersion. All polar molecules have dipole-dipole. And then the best one, the one that I love so much that literally holds life together, is hydrogen bonding. Hydrogen bonding is the strongest intermolecular force, and it gets me excited every time, I swear to God. Like, this one just holds together your DNA, it holds together proteins in your body, it's responsible for building proteins in the endoplasmic reticulum of the cell. And what it involves is a special type of dipole-dipole force where very polar covalent molecules with either a nitrogen hydrogen, an oxygen hydrogen, or a fluorine hydrogen bond can attract to another nitrogen, oxygen, or fluorine in a molecule. So this is like a specific type of dipole-dipole for a polar molecule. So that's just the overview. There's 3 different types. There are a couple others, but these are the 3 main types. There's really like one more maybe that is not as important. So let's begin here. We're going to start with the diagram that helps to explain London dispersion forces. So we're going to start by just showing methane. So I'm going to draw a structure of methane. I'm going to use the wedge and the dash to show the shape of the molecule being tetrahedral. Right, and I'm going to show it with London dispersion forces to another methane molecule. So is methane polar or nonpolar? Right, methane is nonpolar. So the thing is that even though there's no permanent dipole in methane, think of this. Think of the fact that electrons and molecules are always in motion, right? They're always moving in their orbitals, right? And that means that at any one moment, there could be a momentary asymmetry in the electron density. So at any one moment, there could be more electron density on one end of the molecule than the other end of the molecule, just because of the fact that electrons are in perpetual motion. So that means then what we can do is write, like, overall, this is like a temporary, right? A temporary partial negative, right? A temporary, like, kind of dipole, but not a full dipole, where temporarily there could be partial negative charge on one end of the molecule, and therefore on the other end of the molecule, temporarily, for like a fleeting instant, there could be partial positive charge. That means then what can happen is another temporary weak, dipole-like phenomenon can happen, where if this is partial negative, then it can induce a partial positive, right, temporarily on another molecule, which would then make the other end of that molecule partial negative temporarily. So in this way, even nonpolar molecules can exhibit intermolecular forces. And really, I should back up and say, right, that intermolecular forces are like magnetic forces between molecules. You can think of them as like magnetic forces. Molecules stick together, some better than others. When they're nonpolar, they don't stick together very well because they only have this temporary dipole, which isn't a real dipole at all. But as we know about positive and negative, right, still that's enough to sometimes keep nonpolar molecules together and to have them stick together. So remember, right, that positive and negative attract together. That's the electrostatic force, right? One of the 4 major forces of the universe. What's the driving force to change the partial charges? I don't know what you mean by that. Like, I just drew it this way, but they are changing all the time. I'm sorry, I'm still, how would the force suddenly change? I wouldn't say that the force is suddenly changing. Yeah, it's shifting all the time, yeah. It's only temporary because electrons are in perpetual motion, right? Electrons are always in motion. Exactly, the electrons are always moving. And so at any one moment, there could be more on one side of a molecule than the other side, which would then induce, right, negative, right, attracts to positive. So it would induce like the electron to shift over here, right, from this side of the molecule, and then that would attract together. Yeah. Okay, so then examples. So then which molecules that we've drawn today, right, or on our previous chart are, and I'm going to split them up into polar and nonpolar. So what's a polar molecule that exhibits London dispersion forces that we have from our, and we'll talk about the uncharged ones. What's a polar molecule? The ones that are not ions. From our other worksheet, water. Water, what's another polar molecule from our other worksheet that is not an ion, that's not an ion? Yep, NF3. Good. Was CO2 polar or nonpolar? CO2 is a good one to place in here, but remember that for CO2, the bonds actually, the polar vectors actually did cancel. And so CO2 is actually a non-polar molecule. Yeah, cool. Another non-polar molecule that we drew on our chart already would be what? Yeah, CO2 is nonpolar. Right, N2, good one. CH4. Yeah, cool. Good. Great, everyone. Okay, good. Those are examples. So all of these do exhibit London dispersion forces, right? It turns out that the nonpolar ones, though, that's the only force that they exhibit. So are these solids, liquids, or gases at room temperature? Carbon dioxide, methane, nitrogen, yeah, they're all gases, exactly, right? Since they're non-polar, so only London dispersion. And since London dispersion, right, is such a weak force, it's only these temporary induced dipoles that are like, kind of sticking together, right? That means then that these molecules are not highly attracted to each other, like in a pure sample. So that means that they are gases at room temperature. London dispersion is weak. A weak IMF is not international, whatever, monetary fund, but intermolecular force. Nitrogen is not a greenhouse gas, but yeah, carbon dioxide and methane are, right? Nitrogen is necessary for life and it's present in the atmosphere, but it is not a greenhouse gas. But yeah, carbon dioxide and methane are. Thank you for pointing that out. Okay, you know what's cool? Here's an application of London dispersion forces. So in fact, I don't believe they do. Do they get broken up by UV? Oh, I don't know. I think the problem is that they don't get broken up by UV and that they accumulate, George. Right? If carbon dioxide got broken up by UV, that'd be awesome because it wouldn't be accumulating the way it is. Same with methane. Okay, George? All right, so check this out. So here's a gecko. Geckos are cute. That doesn't look like any gecko I've ever seen. The ones I see are like pink and translucent, but it's still cute. And look at that. Look at all those little hairs on the little gecko paw, right? And we can see, right, that although any single interaction is weak, London dispersion forces are actually strong when there's many, many, many of them. So, for example, geckos stick to walls and ceilings by London dispersion forces, right, between the surfaces and the 500,000 tiny hairs on each foot. So it's just London dispersion. It's nonpolar molecules, right, exhibiting forces with the electrons, right? So here's a macroscopic representation and example, right? And we can go all the way down to the submicroscopic representation. Yeah, chlorine does, George. Chlorine does. That's true. Right. Chlorofluorocarbons do, George. They mess up they interact with ozone and disrupt it, and they deplete it. So in the diagram in the middle, is that showing movement? This one here is showing attraction. That attraction is called London dispersion force, specifically. It is a type of electrostatic force. It's an example, I should say. It's an example of the electrostatic force, yes. It's an example. All right, so another example of the electrostatic force is when we talk about dipole-dipole between polar molecules, okay? So dipole-dipole forces right, exist, and I'm going to show the diagram here, between polar molecules. And so this is the attractive force between permanent dipoles. So just like magnets attract to each other with their opposite poles, molecules also attract together with their opposite poles. So if we look at a model or like a diagram, right, of HF, for example, right, another HF, can we draw a dipole vector for the bond between hydrogen and fluorine? Can we draw a dipole vector? Yeah, Vanessa, it's two of the same molecule, but it doesn't have to be. It doesn't have to be. London dispersion can happen between all molecules, but it doesn't, it can be with two of the same molecules, but it can be different molecules too. Can I draw a dipole vector here? Can I show? Yeah, I can. Toward which atom, hydrogen or fluorine? Right, toward the fluorine, right? Fluorine is way more electronegative, right, than hydrogen. So definitely a polar bond there. Yeah. So I can draw my dipole vector toward the fluorine. Okay, and since I can do that, over here there was no permanent dipole, right? I'm not showing a dipole vector on those, right? But since I can do it over here for this polar molecule, then I for sure have a partial positive charge on this hydrogen, permanent. A partial positive on this side of the molecule, permanent. Right, these are now permanent. Right, and that means then on the other end of the molecule, right, on the fluorine side, we've got a partial negative. On the other fluorine side, a partial negative. So this is a strong attraction. Because these are like, oh, yeah, there might be you know, a moment in time really quickly where there might be some electron density, you know, more on one side than the other, and then that might attract to another molecule, and okay. But over here, for sure, HF, right, these molecules are going to be able to attract to each other. You know it's partial positive when it's less electronegative with the positive end of the arrow on the partial positive. And you know it's partial negative toward the more electronegative atom. More electronegative. Fluorine has a 4.0, hydrogen is 2.1 electronegativity. And so, right, so we can show, so that's the diagram, and then we can show some examples. Okay, let's show water, right, the two polar molecules. Let's show them interacting dipole-dipole together. So we can do water H, and I'm just going to draw it like a different way than we're used to seeing so that we know we can draw it any way we want to. Right? And I can actually show like over here, we've got our permanent, right? Oh, I wasn't showing that, but yeah. Right? We have our permanent showing the molecule is polar. There's only one polar bond here, so the molecule is polar. And we can also show water, right? Like this. Water is a polar molecule with more electron density, right, toward the oxygen. So we can draw another water molecule. Again, with electron density, right? The overall polarity of the molecule has more electron density toward the oxygen. So that permanent dipole means that on this side of the molecule, there's partial positive. On this side of the other water molecule, there's partial positive. Attracting permanently to the partial negative on the other side of the molecule, which this side of the molecule attached to another molecule. A permanent dipole means there's a strong, right? I meant to write that up here. Strong interaction. Strong attraction. Yeah, exactly. So going back to the electronegativity chart, which is on Canvas, and which most likely is in your book. I don't remember, I haven't seen one. But here is the electronegativity chart, right? Fluorine is way more electronegative than hydrogen, right? So that difference in electronegativities is 1.9. So for sure that's a polar bond, and for sure fluorine, for sure fluorine has more electron density toward it. Same idea for oxygen and hydrogen. Oxygen is more electronegative than hydrogen. Yeah. H2O, yep. Water is London dispersion and dipole-dipole, exactly. Exactly. So that's the thing. Think of it this way. We're gonna kind of leave off with this. So you can think of this as like kind of a hierarchy where if you have a molecule that displays hydrogen bonding, it also displays dipole-dipole and London dispersion. If you see that a molecule displays dipole-dipole, it also displays London dispersion, right? And if you see London dispersion, you have to look in the molecule, okay, and see, is there more, right? London dispersion, you can write down for anything and you'll at least get a point, because again, all covalent molecules display London dispersion because all the electrons are constantly in motion, leading to perhaps a temporary asymmetry, leading to a weak little attraction between these temporary, you know, non-dipoles, but kind of dipoles, right? And yeah, you have to see if it's polar. It'll also display dipole-dipole. And we are getting to hydrogen bonding, the best one next time, saving the best for last. Let's see. Yep, more electron density, partial negative, exactly. Right? Electrons are negative, and so if there's more electron density, there will be a partial negative there. You're welcome, you're welcome. I know, right? I haven't heard from many of you during lectures, so it's pretty cool, huh? I know. Let's see, I'll screen share. I also want to show you one thing. If you don't mind just hanging on for another minute, I know you're about to go, but real quick, let me screen share. And again, reminder, before we sign off, you need to write, oh, I erased it, but you need to write something in the comments so that you get credit for participation if you haven't already, okay? So screen sharing, let me show you the electronegativity chart. Okay. Modules. Oh, there's my house. Hello. Modules. And we're in, so that stuff is in week 8. So down in week 8. Oh wait, no, we learned about that last time. So week 7. electronegativity values. Okay, everybody. So week 7, excuse me, week 7, right here. Okay. All the chart that we were just working on earlier, right? The first chart today is right here. Oh, I said week 8, didn't I? I think I meant it was in week 7. Sorry about that. But here's the key to the chart. The colors are different because I change it every semester, but the idea is the same. The chart for molecular and electron geometry is here. Oh, I already have it. Oh yeah, here it is. Okay. Make sure that you're using that to determine the shapes of everything and the electron geometry, right? And then here is the oh gosh, here's the electronegativities. Right here in week 7, electronegativity values. Right there. Oh, and you have the fun one showing the relative like heights of the elements, like in regard to their electronegativity. Okay, awesome, everyone. Thank you so much. I'm so glad that you liked it. I'm happy that you're all here. Thank you. Thank you. Let me stop share and just sign off here. Yes, everyone have a wonderful day. Thank you so much for being here. And I'll see you on Thursday. And you're having your quiz right before lecture like normal. It'll start at 11:15 for 15 minutes, and then sign on to Zoom. And the instructions for the quiz will be available tomorrow late morning. And also we do have open hours right today, right at 1:15. And then we also have open hours at from 4 to 5 today. So I'll be here on Zoom at 1:15 and 4. So I'll see you all then. Bye. Thank you so much, everyone. Gracias. Que tengan un muy buen día.